Hi, it's Mr. Duffy. Welcome to physics. Today is going to be our first lesson in our Unit 2 of two-dimensional motion. Today we're going to be talking about adding vectors. So let's go ahead and get started. So again, this unit is about motion in two dimensions, in which case we have, again, object maybe moving horizontally and vertically at the same time, or it might just be, again, moving in a direction maybe like northeast or northwest or, along those things. You have two directions for its motion. This is again different from last unit, which we talked about one-dimensional motion, maybe an object just moving horizontally or just vertically. But we need to refresh ourselves on what the terms vector and scalar mean. We also talked about this last unit, but again, scalar is a quantity that only has a particular magnitude and amount, no direction associated with it. Vector, on the other hand, the vector has a quantity, an amount, and a direction in which case the object is moving. So again, this is nothing new. For example, 25 miles per hour south, the magnitude is 25 miles per hour, and then the unit, the direction would be south. 9.81 meters per second squared down, that would be gravity. Again, not anything new. Vectors can be represented by arrows. Now, we didn't necessarily do a lot of that in last unit because, again, the objects were just moving in one particular direction, maybe down. But sometimes, again, I did have you draw some diagrams, especially if the object was moving up and down um, or it changed its motion in some way. But again, vectors can be represented in arrows where the magnitude is indicated by the length of the arrow, and then the direction obviously points. In this case, if it's pointing to the right, the object is moving to the right. Now, what that lends us to have is if we have objects moving multiple different directions, we can have vectors and add them together. Again, it could be a vector for displacement, maybe again, it change in position. It could be a vector for velocity. Again, different vectors meaning different things, but again, can they be added together graphically? The answer to this, yes. We can take these vectors and add them together, but we have to do it in a specific way. So when we add together a vector, we have to add them together in what's called the head to tail method. So the head of one vector, the arrow of one vector, has to match up to the tail of the other vector, in which case, again, it tells us um, the overall resultant from the start position to the final position. Again, whatever that those vectors represent, whether it's the initial velocity and final velocity or whatever, or again, initial position, final position. Again, that resultant would be what is left over afterwards. Over here on the right, I have a diagram of a person walking from their house to their friend's house and then to school. You kind of can see those are position, displacement vectors. In which case, again, they go from A to the yellow house to then to the yellow house to school. But the overall resultant would be from your starting position to your ending position. So again, this person started at their house and ended at the school. The resultant vector is the dotted line. Now, the next thing I want you to kind of realize is if I add vectors together in this head to tail method, does the order in which I add them matter? Now, again, the sequence might make sense most if you're talking about in like the last example, you started your house and you went to your friend's house to pick them up, and then you walked to school together. The order there kind of like just follows the sequential order of what you actually did. But again, would it really matter if we measure the overall position from your friend's house to your house and then your friend's house to school again and added them together differently in reverse order? Would that make the overall resultant displacement different? And here's what I would challenge you: these two vectors that I added together. What I'm going to do is I'm going to draw a resultant vector with a red line. I'm going to do the same thing over here, in which they were added together in the opposite order. And what I'm going to do is I'm going to then bring them together right next to each other. And I would ask you again, do these vectors look the same? And for the most part, yes. Maybe I didn't quite draw it perfectly, but for the most part, yes. These are both about the same length of arrow and they're both pointing in the same direction. So it does not seem to matter the order in which I add my vectors together. I'm still getting the final resultant to be the same. Now let's take a look at this again. I have three vectors that I'm adding together, and we'll do the same exact thing. Again, my resultant vector is from where I start to where I end. So I'm going to do that in each one of these cases. They were all added together in head to tail method. And so now I can take each one of these individual resultants. Okay. Ungroup that. Okay. And then I can compare them. They all look roughly about the same length and they're, again, pointing in the same direction. So this, again, further verifies that it does not really matter what order I add my vectors together, as long as the important part here is I have to add them together in head to tail method. If I don't do that, then I'm not going to get the right answer. So this brings us to our first example problems. I have these five vectors here, A, B, C, D, and E. And I want to add the vectors together. Again, I'm just representing adding them together in head to tail method. I'm going to add A plus B plus D. So vector A is completely horizontal to the west. B is, I would assume, a roughly 45-degree angle in that magnitude. And then I'm going to add D to it. Okay? Now, that's A plus B plus D, but the resultant, that red line there, would be the addition of those three vectors added together. Again, I could have added them, again, adding them together in different orders, and I would still got the same red line at the end. I guess I just didn't think about this before, but you can liken this to a math problem. If I add 1 plus 2 plus 3, it equals the same as 3 plus 2 plus 1 or 2 plus 1 plus 3. Again, the order does not really matter in this case. Okay, now I'm going to add A plus C plus D. So we've got A vector, C vector is directly vertical, and then D vector is, again, kind of like a 45 there. My resultant is from the start to the end. That would be the addition of those three vectors. Finally, B plus C plus E. B is a 45 roughly, plus C, which is a vertical, and then E, which is totally, again, horizontal. My resultant vector would be something along those lines. Now, these are rough sketches of what these vectors are added together. We're not solving for any information right now. We're just again trying to represent those vectors being added together. And I'm trying to do my best to make sure that I'm representing the direction that they're going and the magnitude from the given problem. But again, it's not perfect. If I wanted it to be perfect, I really need to try and make ensure I follow some type of scale. And again, I would need to use maybe some like graphing program or at least graphing paper to be able to show and solve for a vector addition using a scale system and using arrows. So if you want to do that, which again we won't really do this very much, but again, if you want to do that when you're drawing vectors to calculate the resulting vector, you need to choose a scale and stick to it. For example, if 1 centimeter on your scale is representing a velocity vector, then 1 centimeter might equal 10 kilometers an hour, and you might draw an arrow like again this blue one here. But if you want to, again, something's going 20 kilometers an hour, your vector arrow needs to be twice as long as that. So again, you need to stick to a scale, and again, you would have to measure your directions using a protractor. So let me just give you an example of this. Um, Adding together vectors and doing it graphically. Let's imagine we have this problem. An archaeologist climbs the Great Pyramid in Giza, and the pyramid's height is 136 meters, and its width is 230 meters. What is the magnitude and the direction and the displacement of the archaeologist after he's climbed from the bottom of the pyramid to the top of the pyramid? So basically, again, starting here at the bottom of the pyramid and climbing to the top of the pyramid, what's his overall resultant displacement in position? Now, again, if we're doing this graphically, we're again drawing this out, we would need to set up a scale, in which case maybe we would set 1 centimeter equaling 10 meters on the real pyramid. We could, again, set up on a graph piece of paper, and we would draw out, a line going, directly horizontal to the east, let's say, and I'd measure it out, again, to be like 15.5 centimeters. That was it was 155 centimeters. Oh, sorry. I think it was something like that. Anyways, I'm not 100% positive, but we'd set out that measurement to again equal that on the scale as far as the base of the pyramid, and then as far as the height of the pyramid, I believe it was 165. So I think it'd be 16.5 centimeters there as the height. So I would draw those two out on my graph paper in the correct scale, and then I would measure my resultant using a ruler, and then I could compare that and compare that scale and again convert it. Then I could also measure my angle here using a protractor to solve for the vector addition problem. But again, setting to a scale and whatnot is possible, but more than likely, it's just easier to do the math for it. So in which case, if we set up, knowing that this makes a right triangle, set up the diagram, but not worrying about drawing it to scale, just again remembering again what the sides are, we can use the Pythagorean theorem to solve for the hypotenuse, which would be side C. In which case we have a squared plus b squared equals c squared. That's the Pythagorean theorem. Our side lengths are 136, 155. Sorry, I was off on the last slide. But anyways, that would equal a hypotenuse of 178 meters. So that's how far the archaeologists climbed, again, as they climbed the Pyramid of Giza on the outside. Now, that only is portion of it. Remember that vector must have magnitude and direction. So we would also need a direction of the hypotenuse, and that would be done by using, again, another trig function. Instead of using the Pythagorean theorem, now we would use a tangent. And so again, tangent would get us our angle here on the bottom, the direction of the displacement, and that comes out to be 49.5 degrees. So again, much easier to do mathematically, I think, than actually setting it up and doing it graphically. But again, having a rough sketch is important, but it doesn't have to be, again, perfect unless you want to do, again, measure it at the end. Okay, now, a couple more slides of notes. Every vector that is in 2 dimensions, that again means that it's not completely horizontal or not completely vertical, would have some portions in which case it's going in the x direction and the y direction. So again, if you're traveling in northwest, for example, you would have some x component to your motion and some y component to your motion. Again, last unit we did not have that. We had objects moving completely horizontal or completely vertical, and no mixing of vectors of components. And we'll still have some of those in this unit as well. Some portions of a vector might again just move west or just move south. But again, most of our stuff is going to have at least some two-dimensional motion. So again, remember that if something is just moving vertically, it's only going to have y components, and if something is moving totally horizontal, it's just going to have your x components of motion. And again, that's what like last chapter was like. Now, what's going to come into play though is that again, sometimes we're going to have multiple vectors being added together, and adding up the x and the y components of more than one vector will give us the same resultant vector. Now, again, this is much easier, much simpler to do than actually drawing it out. It's much easier to do mathematically. So again, I would not use graph paper and whatnot to set it up. So again, same diagram here. Another way that this adding your components becomes useful is when triangles or when vectors, when they added together, don't immediately make a right triangle, we would have to use the x and y components to actually solve and make each individual portion right triangles to solve for it. Like again, that Pyramid of Giza example that I gave you earlier, that immediately made a right triangle, and so we could solve for it using the Pythagorean theorem. But if it doesn't immediately make a right triangle, we cannot use the Pythagorean theorem or the trig functions. We have to, again, resolve it into right triangles. So let's take a look at this example here. I'm going to take the x components from the first vector, and I'm going to add those together. And then the y components from the other vector, again, add them together, head to tail method. Okay. And you can see that basically we get an overall vector from the start to the finish that does end up making a right triangle. So again, the original portions themselves, each individual vector itself didn't make a right triangle, but when you add it together, when you add the x components and the y components together, you're going to get a right triangle because the x and the y always are at right angles to each other. So again, we could solve for the resultant vector, the green vector there, the hypotenuse of the triangle, using the x and y components. We'll do an example from that here in a second. Okay, so this example problem is more like the archaeologist problem, which I did earlier. But while following the directions on a treasure map, a pirate walks 45 meters north and then turns and walks 7.5 meters east. What straight line displacement could the pirate have taken to reach the treasure? So these problems really you kind of always need to start off with by drawing diagrams showing those vectors. And what I would recommend is really try and stick to some type of scale. It does not have to be perfect, but we want to try and get it to be close. So the pirate walks 45 meters north. That's my first vector. It has a magnitude, and again, I drew it north, so the direction, magnitude and direction. Then they turn and walk 7.5 meters east. Again, I would try and stress, do not draw that line too long because in comparison to the other vector of 45, it's got to be a lot shorter. So the question is, what is the straight line portion that this pirate could have made? I'll try and draw it, a little dotted line, to get to the treasure by moving along that hypotenuse. Now this triangle, this example, again, we have two-dimensional motion because it moved vertically and then horizontally here, but it immediately makes a right triangle, a 90-degree angle, because they did completely north and then completely east. So in which case I can jump right to using trig functions, Pythagorean theorem to solve for it. What I'm going to do first is, since I've got two sides, I'm going to actually find the magnitude by using the Pythagorean theorem. A squared plus b squared equals c squared, where a squared is 45 meters. I don't necessarily write out meters. Okay. So 45 squared plus 7.5 squared equals c squared. Now, I'm going to have to do this in my calculator. So 45 squared plus 7.5 squared, that comes out to be 2081, but then don't forget to square root that afterwards. I get a value for C, which is 45.6 meters. And that would be my answer for I'm not done yet, but that is my answer for portion. And again, I should always double check the hypotenuse of the triangles should always come out to be more than its individual sides, and it did. But it's not much more, but it is more. Okay, so again, like I said, I'm not done yet because we would need a direction as well. So every vector should have a magnitude and a direction. We only have a magnitude. We need to find that angle that the pirate should indicate the direction that the pirate should walk. To do that, I'm going to use tangent. And again, we've already done some trig problems already. So I'm going to use tangent, which again is my opposite over my adjacent. And I could use any trig function at this point in time because I've got all three sides, but I would try and focus you on using tangent because opposite and adjacent were given to me in the problem. So I really should try and use those in case I messed up with my hypotenuse in my first problem. So anyways, the opposite side is 7.5 meters and the adjacent side is 45 meters. So I'm going to do inverse tangent to find my angle, 7.5 divided by 45, and I get a angle of 9.5 degrees. And again, that's not totally entirely done yet. It is the angle measurement, but we also need to include the coordinate system. So north, south, east, and west here, because again, 9.5 tells me that the portion of the triangle, but doesn't really give me necessarily a direction. And so what I need to remember is that I started at completely north and I went east of that. So it's 9.5 degrees east of north. And that would be my direction. So that's the pirate. The pirate should walk 45.6 meters at 9.5 degrees east of north to get to the treasure, instead of just, again, walking directly north and then directly east. Okay, so this problem set up in the case of making a right triangle immediately, but let's take a look at this problem, which it will not. In this problem, we have a hiker. A hiker walks 27 kilometers from her base camp at 35 degrees south of east. The next day, she walks 41 kilometers at a direction of 65 degrees north of east and discovers the Forest Ranger's tower. How far is the Forest Rangers? Find the magnitude and direction from the base camp to the Forest Ranger's tower, which would be the red line on my diagram. So again, I pulled the information out of this problem already to kind of, again, start us in this problem a little faster. And I've also already drawn a diagram. Now, when you're looking at this diagram, you might say, okay, well, that's not any different from the last problem that we did. It makes a right triangle. And I would caution you against just initially, making that judgment. It does very much look like a right triangle, but this angle here that looks like a right angle is actually only 80 degrees. So it is not a right triangle and not something that we could just use the Pythagorean theorem on right off the bat. What we have to do is we have to resolve each individual vector into its x and y components. So you can draw this in a variety of ways, but the way I'm going to draw it is I'm going to make a triangle in green for the first vector. It goes south, then it goes east. And then for the second day's motion, I'm going to continue again. I'm going to draw this triangle. It goes east some more and then north. So we can see how we get, again, two right triangles from our initial motions. The final resultant vector, which is red, also can be resolved into the addition of the components. It can also make a right triangle there, in which case we can again find that's going to the red triangle is going to be our final answer. That's where we want to get to entirely. So let's start off with the first day's motion, the green triangle. Now, this first day they walk 7 kilometers. That's the hypotenuse of the triangle. And they do it at an angle of 35 degrees south of east. So the angle here is 35 degrees. That's this one that I'm drawing in the graph. So you'll notice first off that that's not even in my triangle that I drew personally when I was setting up this problem. But what we should know is that, again, the angle that they gave us in the problem, which again is 35 degrees, plus the other portion of this triangle would add up to 90. So again, 35, 90 minus 35 is 55 degrees. So this angle here on the inside of, which is actually in my triangle, is 55 degrees. And also the 35-degree angle would have been down here on that triangle as well. So again, it wasn't, you just got to make sure you put the correct angles in the correct spots. Now, with those pieces of information, with those angles and the hypotenuse, I should be able to solve for my x and my y values. So this is my x in the green triangle and my y in the green triangle. Now, to do that, we're going to have to use sine and cosine. I'm going to use the 35-degree reference angle and do sine of 35 degrees is equal to my opposite side, which my opposite side is y, over 27. And then solve for my x component of the green triangle. Cosine of 35 equals x over 27. That'll allow me to, again, solve for my x and y values. Give me a second to solve those. 15.5 kilometers is the y component, and cosine of 35, 27 is 22.1. I'm just going to leave those there. I'm not going to transfer them onto my diagram because that's getting a little cluttered. So now I'm going to do the same thing on the blue triangle to figure out, again, the x and y components. The distance traveled on the second day was 41 kilometers, and that's the hypotenuse again. We want to solve for the x and y values here as well. What it gave me in terms of direction is 65 degrees north of east. And that one actually does fall in the triangle, in which case that's the bottom left angle. So again, I don't have to solve it. That's exactly the 65 degrees north of east is that measurement. So now I can, again, use that as my reference angle. And again, sine and cosine are going to allow me to solve for my x and y values. So I'm going to do sine of 65 degrees is equal to my opposite, which would be y over 41. And then cosine of 65 equals x over 41. Okay, let me give you a second again to solve those. My y value is 37.2, and cosine of 65 times 41 is 17.3. Okay, so now I have my x and y values, and I actually was thinking while I was in this problem is that I made a mistake in my green triangle in the fact that my y value here is actually negative because it's going to the south. So that's one thing I didn't really include before, but it is negative. And that will be coming to play. It didn't really matter too much above, but it will come into play now when I'm trying to add my x and my y values together. So I'm going to take my x values, add those together. They're both positive. They're both to the right. So my first x value is 22.1 kilometers. And I'm going to add to that my other x value, which is 17.3 kilometers. And that's going to be my overall x total, or my total displacement in the x direction. 22.1 plus 17.3 is 39.4. And then in my y direction, I'm going to do the exact same thing. Negative 15.5 kilometers plus my y from the second day's motion, which was 37.2 kilometers. And that's going to equal my overall displacement. It's 37.2 minus 15.5 is 21.7 kilometers. Okay, now those are my x components and my y components of my resultant vector. I'm still not done with this problem. So I had to plug those in and then solve for the final 21.7. I'm going to put that on my red triangle up here on the top. And 39.4 is my x component. And now you can see I have the two sides, my x value and my y value for my resultant triangle, the red triangle. And now I just need to solve for the magnitude of the red triangle, in which case I can solve for the magnitude by using Pythagorean theorem. A squared plus b squared equals c squared, and I'm looking for c, which is the hypotenuse of the triangle. So again, my a squared value is 21.7 squared plus 39.4 squared equals c squared, and then again, I'll take the square root of all that to get c, my final answer. So c would equal, give me 1 second to solve that. .9. Actually, it rounds up to 45. 45 kilometers. Okay, now that is, again, I'm not done with the problem yet. That is the magnitude of my displacement, but it is not the direction. And so now I need to get an angle measurement. And so I'm going to get this angle right here in my right resultant triangle. To do that, I guess I'll just do tangent. So let's do it up here. Tangent of theta equals my opposite side, which is 39.4 divided by 21.7. And at this point now, I could have used any trig function, but I'm just going to use tangent. So I'm going to do the inverse tangent to get an angle. 39.4 divided by 21.7. Okay, that gives me an angle of 61 degrees. Theta is 61.2 degrees. And again, that is not entirely, that gives me some information, but I need to, again, put the coordinates to that. That would be east of north. So you can see that in this problem, we can solve for the resultant vector by adding x and y components from the original vectors together to figure out the total x, the total y, and then using that information to resolve for the final resultant vector, magnitude and direction, when we don't immediately end up with a right triangle. Like in this example, we didn't immediately start with a right triangle to solve for it. Hopefully addition of vectors makes sense to you when we're talking about two-dimensional motion, and thank you for watching.